SwayamPrabha. Digital India. Educated India.
Good morning everybody. Today we will discuss about transient conduction. Consider a hot metal initially at a temperature T0, quenched by immersing in a liquid at temperature T infinity. Now T infinity is less than T0. The essence of lump capacitance method is the assumption that the temperature of the solid is spatially uniform at any instant during the transient process of cooling. Now, in such a material, we can perform the energy balance, rate of change of internal energy of the solid equal to rate of heat loss at the surface of the solid. So we can write the equation rho Cp into volume of the element, d temperature, d time rate of change of temperature, equal to minus H, the heat transfer coefficient, area into T minus T infinity. T infinity is the local temperature. This is like, capacitance in series with resistance. Now from here we can write d temperature, d time equal to minus HA rho Cp V T minus T infinity. So d theta dt equal to minus HA divided by rho Cp V into theta, where theta is T minus T infinity. So we can write from here d theta by theta equal to minus dt by tau, where tau is the time constant, rho Cp V volume of the material divided by H into A. If we work out, we will find that the final dimension will be second. So basically time constant is second. It can be expressed in second, and time constant is a very important parameter for all temperature measuring devices. As I said, if we do the analysis fundamental dimensions, it will be second, and lesser the value of time constant is always beneficial, because faster will be the response of the device. Now we are not directly considering that, but just I mentioned about this parameter time constant, and this is a very important parameter in all temperature measuring devices. Here we can write d theta by theta equal to d t by tau, and after integration we can write ln theta equal to minus t by tau plus C1, and we know the boundary condition at t equal to 0, theta equal to theta naught. temperature, see theta is defined by T minus T infinity. So initially temperature was T naught everywhere. So theta is theta naught. Applying this boundary condition at t equal to 0, theta is theta naught, we can find out C1 is ln theta naught, from where we can write ln theta by theta naught equal to minus t by tau, or theta equal to theta naught into e to the power minus t by tau. Time constant tau also gives us the idea as to how the ambient temperature is reached. You can see theta by theta naught versus time. If we plot, we can see that at every time constant value tau, how it varies. Now, also the concept of Biot number is introduced here, or Biot number is introduced here, which is given by H, the film heat transfer coefficient, into characteristics length by the thermal conductivity of the solid. So we can rearrange the terms as HL into A divided by KS into A, which can further be rearranged L divided by Ks into A, entire quantity divided by 1 by HA. Now 1 by HA is fluid film resistance, or resistance to convective heat transfer, and this is resistance to conduction heat transfer, or conductive resistance. The aforesaid transient analysis is valid for this Biot number or Biot number much less than 1. The temperature gradient within the solid is small. So as we said, it is uniform. That's what we will consider. That means T x comma time temperature distribution initially is basically uniform, so we can write T is a function of time. The temperature difference is between the solid and the fluid. Fluid will be having one temperature, surrounding fluid, and solid will be having one temperature, representative temperature, and we'll consider how the heat transfer takes place, and the solid temperature reduces gradually as a function of time. If the following condition is satisfied, the error associated with the lumped capacitance method is small. That means if Biot number or Biot number is less than much less than 0.1. Now from the equation theta equal to theta naught into e to the power minus t by tau, we can write that the exponent is basically given by HA time divided by rho Cp into volume. And here HA time divided by rho Cp into volume, we can rearrange. We can write HL by Ks. We bring one L here. Actually, if we look at the dimensions, A is L square and V is L cube. So as such, here we have HT divided by rho Cp into L. A and V, that will produce 1 by L. But here what we are doing, we are writing HL by Ks. So we are bringing one L extra. Then we are again multiplying it with by Ks. Ks and Ks will cancel out, divided by rho Cp into 1 by L square. So from this L square and this L, we'll get 1 by L, which was our original quantity. A by V is 1 by L. So this is Biot number into alpha T by L square, and also this is a non-dimensional group, and its name is known as Fourier number. So Fourier number is alpha T by L square, and it is nothing but sort of non-dimensional time. And we can now write theta equal to theta naught e to the power minus t by tau. Instead of that, we can write theta equal to theta naught e to the power minus Biot number into Fourier number. Now we will consider analysis of one-dimensional transient conduction in a 1D slab. Why 1D slab? Because this slab is such that its y extent is extended to infinity, z perpendicular to the plane extended to infinity, and the variation in x will only be considered. So governing equation is rho Cp del T del temperature equal to K del to T del x square. At x equal to 0 and x equal to L, temperature is Tc for finite time. That means after the time of interest, the temperature of these two side walls are Tc. But initially the temperature distribution is different. It will, after getting cooled by the local ambience, its temperature will be Tc. And at T equal to 0, temperature is T naught, and we have seen it is between x greater than equal to 0 less than equal to L. That means within this domain 0 to L. And theta is T minus Tc, and theta naught is T naught minus Tc. We assume the solution theta is a function of x and t. So uppercase X is the solution of the x dependent part, and gamma is the solution of time dependent part. So del theta del t, which is del temperature del time, we can write x into gamma dot t. Gamma dot means the d gamma dt. Del 2 t del x2 is x double prime x into gamma dot t, which is del 2 theta del x2. So we find then, after substituting in the governing equation, which is del theta del t equal to alpha del 2 theta del x2, is alpha x alpha x double prime double derivative of x component into gamma equal to x into gamma dot. So we can rearrange gamma dot divided by alpha into gamma equal to x double prime by x, typical separation of variables, and this is equal to, we can say, lambda square or c, separation constant. Now left hand side is function of t only, and right hand side function of x, typical properties of separation of variables. Now this c, what separation constant, we do not know whether it will be positive, negative, or even it can be imaginary. So if first let us assume c is imaginary, then solution will be of this form. and which is oscillatory. We really, do not expect in such a cases any such oscillation. Now C can be positive. Then solution can be a solution. If C is positive, solution will be something like this. And here also we can see that gamma will be equal to gamma naught e to the power alpha Ct. So this is also growing in time, and this is not possible because initially it is at a higher temperature T naught and it is being cooled, and after the time interval we get the side wall temperatures Tc, so it is not really growing. Now we consider 1 by alpha gamma into del gamma del T. This quantity is minus lambda square. If we assume it minus lambda or accept this as minus lambda square, this separation constant, we can see the solution becomes gamma equal to C1 e to the power minus alpha lambda square T, and this is acceptable. So basically we can now say that separation constant of this gamma dot divided by alpha gamma equal to x double prime by x equal to minus lambda square. Now if we say this is minus lambda square, then the solution will be C2 sin lambda x plus C3 cos lambda x. d2 x dx2 divided by x equal to minus lambda square. That means d2 uppercase x dx2 equal to minus lambda square into uppercase x, and solution of this is uppercase x as a function of x, C2 sin lambda x plus C3 cos lambda x. So this is the spatial solution, space dependent part, and this is the temporal part of the solution. Now we can combine them as a product, and that total solution is e to the power minus alpha lambda square T into C1 and C2 and C1 and C3. After multiplication we get another constant a cos lambda x plus b sin lambda x. Now at x equal to 0, for time greater than 0, theta equal to 0. That means T becomes Tc. At x equal to 0, that we have already seen in the geometry, at x equal to 0, T will be Tc. So then that means in this equation, if we substitute x equal to 0, we will get a e to the power minus alpha lambda square T equal to 0, which will give us a equal to 0. So that means now theta a equal to 0, so it will be a to the power minus alpha lambda square T into b sin lambda x. Now second boundary condition is at x equal to L, for t greater than 0, again theta is 0. That also we have seen. Here also it is Tc. Now since t equal to Tc, theta equal to 0, so we can now write e to the power minus alpha lambda square T b sin lambda L equal to 0. Now this is only possible for two cases, either b equal to 0 or sin lambda L equal to 0. If b equal to 0, solution becomes trivial solution. So it will not go through that route. We will take sin lambda L equal to 0. And if sin lambda L equal to 0, then lambda L equal to we can say n pi, where n equal to 1, 2, 3, up to infinity. Therefore, theta becomes then Bn e to the power, so basically lambda is n pi, so b to the Bn into e to the power minus, instead of lambda n, we can write now n pi by L square into alpha t, and sine lambda L, we can write sine n pi x by L. So this becomes the solution now, where Bn is still unknown. Now this equation must satisfy the initial condition. That means theta equal to fx at t equal to 0. So if we substitute t equal to 0 here, we will get theta naught, because at t equal to 0, temperature everywhere is T naught. That's what we said. Temperature would be T naught everywhere at t equal to 0. So it will be theta naught equal to summation n equal to 1, 2, 3 up to infinity Bn sine pi nx by L. Basically, this equality is Fourier sine series. We can very clearly see sine series expansion of theta over the interval x greater than 0 less than L, using the properties of orthogonal functions in the interval 0 and L. So which means between 0 and L, sine m pi x by L into sine n pi x by L dx equal to 0 if n not equal to m. That is the property of the orthogonal function. Now if n equal to m, then 0 to L, this will be sine square n pi x by L dx, and we will be able to write 0 to L half 1 minus cos twice n pi x by dlx, and this will be L by 2. So similarly, 0 to L theta sine lambda n x dx will be then, if theta is multiplied by sine lambda n x dx, and this is also multiplied by, from this equation, theta equal to summation over Bn sine n pi x by L. Theta we multiply by sine lambda x and perform the integral dx between 0 and L, and this part also we multiply with sine lambda nx dx and integrate between 0 to L. And when lambda n and lambda m are same, then we have already seen that this integral sine square n pi x by L dx is L by 2. So Bn sine square lambda n x dx is Bn into L by 2. So Bn will be then 2 by L into this. If we equate with this, 2 by L multiplied by 0 to L theta naught sine lambda n x dx. So Bn is twice theta naught by L, 0 to L, sorry, 1 theta naught has been extra. It should be dropped. So twice theta naught by L, 0 to L, sine n pi x by L into dx. 1 theta naught should be dropped from here. I'm sorry, 1 theta naught we can drop. So then we can write Bn equal to twice theta naught by L into L by n pi minus cos n pi x by L. This is integration of sine n pi x by L dx, and limit is between L and 0, upper limit and lower limit. So Bn we can get from here very clearly twice theta naught by n pi 1 minus cos n pi. So theta then becomes, so theta will be then, we have to substitute beta naught in this expression. We have obtained beta naught now. So theta equal to theta naught summation sine, within summation sine we can write 2 by n pi, and theta naught we pull out outside the summation sine, 1 minus cos n pi into sine, we had sine n pi x by L into sine n pi x by L into e to the power minus n pi by L square alpha t. Now beta n is this, we have inserted this here, invoked this beta naught value, beta n value. Now beta n is twice theta naught divided by n pi into 1 minus cos n pi. Now for even n's, this term will be 0. And for odd n's, this term will be 4 theta naught by n pi. So in the summation series, we can keep all the odd terms, because for all even n's, this term will produce 0. So therefore theta becomes theta naught into 4 by pi into 1 by n. So since beta naught is 4 theta by beta n is 4 theta naught divided by n pi, so this whole quantity we can write as theta naught into 4 by pi, and 1 by n we take inside, because this is summation over n, and e to the power minus n pi L square alpha t sine n pi x by L. So theta by theta naught is then 4 pi into summation all odd n's 1, 3, 5 up to infinity, 1 by n sine n pi x by L e to the power minus n pi by L square into alpha t. So finally we can write theta by theta naught equal to 4 by pi summation over n, all odd terms of n will be there, 1 by n sine n pi x by L e to the power minus n pi by L square alpha t, which means what is theta? Theta is t minus tc, and theta naught is t naught minus tc, equal to 4 by pi into summation sine n equal to 1, 3, 5, all odd terms up to infinity, 1 by n sine n pi x by L e to the power minus n pi by L square alpha t. And for a given time and given x location, we can find out what should be the temperature. Temperature distribution is obtained that way. So here we have found the temperature distribution based on the idea that the temperature at the sides of the slab is known, which is Tc, after finite time. However, this temperature Tc is dependent on the ambient temperature and the film heat transfer coefficient. In reality, this Tc will be reached because of the given local ambience, due to which H, the film heat transfer coefficient, will be decided, and also local temperature, the temperature of the ambience will be known. So which is T infinity and H, that will decide finally Tc. Here we have taken Tc as the final temperature which will be reached in a parametric form. But how Tc will be reached, that part we have not done today, and we will consider a complete simulation. That means, considering local ambience and its influence, how the cooling will takes place, and then what should be the temperature distribution. We'll analyze such a situation in our next lecture. Thank you very much. Thank you for your interest. Thank you.